So I want to apologize first, both for myself and for the entire HCI group. You may notice that none of my colleagues are here. One of my students is here, but only one, Jeff Avery, sitting back there. And the reason for that is that at 3 p.m. today, it is the ACM SIG-Chi deadline. And so if I seem stressed, it has nothing to do with you. It has to do with a lot of other things. The other thing that I'll say, because of the ACM SIG-Chi deadline, just in terms of extending that apology, is that this is a talk that I've given before. I gave it most recently just a few months ago at the Chinese Chi Symposium as a keynote. The problem with the talk is that it hasn't really been digested for a general computer science audience. It's more focused on an HCI crowd. I am just at the first going to try and position it a little bit for you, mainly because I'm a little bit hard to characterize as a researcher. I think most of us know HCI is a pretty broad field. It sort of spans all the way from low-level modeling of motion all the way up to, sort of more sociological, qualitative studies of design. The thing about me as a researcher is that I actually span that entire space in HCI. So there's like a Chi 2017 and a Chi 2016 paper of mine right up there, and those are papers that I did with one of my students in each case. And they go from sort of low-level models of user kinematics in touch-based interfaces along curved constrained paths, all the way up to learning from green designers, analyzing green design as a form of discursive practice. And this is essentially the full range of HCI, and it's all part of what I do. If you were to sort of characterize me, you'd say I'm probably an empiricist in that I like to observe reality and develop understanding from it. And whether that's based on the scientific method or qualitative data or developing models of user motion and validating them or any of these other things, I enjoy doing that. Now, just to reassure you, the talk that I'm going to give today is sort of focused on vanilla HCI, sort of in the interaction techniques, interaction design space. And it's sort of a series of papers that are pictured there. I'll post the slides afterward. But it's a series of papers that are pictured there that we've published over the last 3 or 4 years that are going to be in this talk and organized in some way, hopefully. So just unpacking the title a little bit. So we're talking about ubiquitous environments right here. Those mean a lot of things to a lot of people. Whether you talk about them as ubiquitous environments, multi-device environments, richly interactive environments, the Internet of Things, anything like that, I don't care. They're all ubiquitous environments. And so we're talking about that. We're looking at interactions in those environments. And the goal of this talk, influenced a little bit by the venue that I was giving it at, is really to talk about some of my work using everyday devices and commodity devices in order to support interaction in those environments. So to try and really use unaugmented environments and everyday devices that people are going to wear and bring to those environments and encounter serendipitously to support various forms of rich, as in expressive, subtle, as in relatively low effort, gestural interactions in those environments. And the last thing I'd like to do is I'd like to just do a call out to 2 of my collaborators on this. Keiko Ketsuragawa, who's a research assistant professor in the school. This work is as much hers as mine. And Jim Wallace as well, who was a postdoc when a lot of this work started, is now a colleague in applied health sciences, cross-appointed to the school. This work is really as much theirs as mine. To give you a little bit of background and sort of describe how I got into this domain of research, I want to take you back to around 2009. I started a collaboration with Google and Mountain View and a guy there named Yong Li in the field of motion gesture interaction. And so we're all familiar with motion gestures. They've been around for a long time. Apple introduced them with the original iPod. Shake to shuffle is an example of a motion gesture for mobile interaction. It's essentially moving a device in order to issue a command to that device. And so I had a PhD student at the time, Jamie Ruiz, who went to Google Mountain View. And he did some work with Yong Li and came up with a delimiter for motion gestures called double flip. And one of the cool things about this work is at that point in time, Google actually owned Motorola. And by late 2010, Motorola had introduced Moto Actions. And one of their gestures, if anyone's got a Motorola phone, they can try it, to turn on the camera is something called the double flip. And so it was kind of cool that work that Jamie did on internship basically went straight out into product through that vector into Motorola. But I think partly because of the success of that work, I had sort of an extensive opportunity to work with Yang on the field of motion gesture interaction. And so we did a lot of work on motion gestures for mobile interaction in things like designing motion gestures, in things like analyzing the cognitive cost of motion gestures relative to on-screen input, because motion gestures leverage proprioception and you don't need to look at the screen. We looked at things like how to teach people to do motion gestures reliably. And more recently, I had a PhD student who became interested in the idea of motion gestures and movement of devices as a mechanism in order to interact with external computation. And so he did some work on interacting with 3D volumetric displays, and he did some work on mass interactions. So in this room, if we wanted everyone to be able to interact with my screen and control it, which would maybe be a bad thing or maybe be a good thing, depending on how much you enjoy the rest of this talk, how would we actually leverage that, given the fact that everyone can't have a pointer on the screen in order to control things, everyone can't click on whatever they want? What do mass interactions look like? What is the space for that, and how do we support it? But this space was really what got me what really started me thinking about this idea of how can we support interaction with external computation that we sort of find serendipitously in the world and we encounter. Smartphones are all right, but you need to pull them out of your pocket. There's a cost for them. But that really brought me to this idea of wearables as an interactive platform to really manipulate computation that you encounter in the world around you, and particularly in richly interactive spaces where we want this computation to be embedded in the environment in a way that we can put behavior together across multiple instances of these devices without needing to go up and configure each one. We don't want to turn on the projector, lower the lights, and turn on the microphone. We want to be able to open our presentation and have all of that happen automatically, ideally, though it really never does. And so that really brought me into this space in terms of why I was interested in working in this space. And the other reasons, there are other reasons that I think that wearables are a good platform for this, or there are specific reasons that I think that wearables are a good platform for this. One of them is wearables are really still a solution seeking a problem that they can solve. So this is Josh Constantine's Apple Watch review after 2 months. This is his entire review. So I love it. It's exactly the way that I feel about smartwatches, in fact. I've had a series of them. I've never liked one enough to keep it on. The only thing I could wear for a long period of time was one of those Garmin Vivo Fits that had an interior battery that actually lasted a year. And the only reason I left it on was because it was waterproof and I didn't bother to take it off. The other reason that I think wearables are a good platform for this, though, is because of some of the challenges of interacting with the Internet of Things that I sort of described earlier. And in particular, when we talk from an HCI perspective about the challenges of interacting with richly computational spaces or the Internet of Things, we talk about the concept of embedded interactions and the challenge of embedded interactions. So what are embedded interactions? Well, embedded interaction is essentially seamlessly integrating the means for interaction into the world. And in general, what that means is that we want sensing and actuation and processing and networking spread out all over the place, and we want to integrate the interaction into users' everyday tasks. We don't want them to have to go up and interact with every individual thing. We want them to be able to issue commands that make sense to them and have all of those things happen automatically. And there are ways that that happens. If you've got a Harmony remote, if you've got a bunch of other things, there are ways that that happens in the real world, but not generally as seamlessly as we would like in every instance. And so just breaking apart some of the problems with embedded interaction, we've sort of got the notion of embedded devices versus interactive devices. And that's what I've been talking about up to this point, the notion that you don't want to interact with an individual device. You want a bunch of embedded devices, and you interact with those things at a higher level. We talk about the notion of the invisibility dilemma. If you're actually embedding computation in the world around you, how can you figure out what the world can do and identify commands in that space that you can actually issue that makes sense? We talk about implicit versus explicit interaction and the Midas touch phenomena. If the world is looking at you all the time, how can it decide when you mean something for the world and when you're just, gesturing because you're really excited about your topic and you want to talk about it? So, And then the last thing is this notion of sensing and tracking. One of my objections, and I'm going to get into this more in a second, that I often have with research that happens in HCI and in gestural input and in richly interactive spaces, is people assume that there's going to be, rich, reliable tracking everywhere in the world, and I actually don't believe that. Vicon systems cost tens of thousands of dollars, so we don't deploy them broadly. People are like, oh, when their price comes down, maybe they'll cost hundreds of dollars, but that still doesn't mean that they're going to be everywhere. And we really need to solve this sensing and tracking problem if we want to be able to deploy things like richly interactive spaces rapidly and easily in flexible environments. And so I really think wearables, because they're something that you own but have rich connectivity, can serve as a platform to address a lot of these things. They're a way that you can issue commands. They're a way that you can understand what you can do. They're a way that you can be explicit about interacting versus assuming that the world is going to be smart enough to figure out when you do want to interact and not. And they're a way that the user can be sensed and tracked relatively richly without needing to spend a lot of money in the world around you. So I've been talking a lot about wearables. But a lot of this talk really is going to narrow down and focus on my research on commodity wearables. And so, just to sort of wrap up, I guess, kind of the theoretical portion of this talk, or the principled portion of this talk, before I get into showing you some pretty pictures and videos. My attitude toward commodity devices is really influenced by the first Chi paper that I read many, many, many years ago. And the paper is called Beyond Being There, and it's by two researchers named Jim Holland and Scott Stornetta, and it's a weird Chi paper in that they don't actually have a system in the paper. It's kind of like a philosophy paper of what we should be doing. And what they were doing at that time is they were talking about video conferencing systems. And some of you in this room remember the 90s. Some of you, may only vaguely remember the 90s. I remember the 90s quite well because I started grad school. The interesting thing about research in the 90s in video conferencing is people were spending a ton of effort on things like, how can you take a video and correct people's gaze so it looks like they're looking straight out of the screen instead of looking down? Or they were investing a ton of time in doing gaze tracking on the screen so you could actually create avatars of people and turn their heads so it was more like you were really in a conference room and you were looking at the person who was talking. And what these guys said is, email isn't successful because you need to write it on a sheet of paper, you need to fold it up, you need to go to the post office and get a letter, you need to send it to someone, and it takes a couple of weeks to arrive. That's not why email is successful. Email is successful because we've taken advantage of the affordances of the platform. And so they said, maybe we should look at what is and how we can leverage that in design rather than trying to replicate reality in some weird way. And so that's always really stuck with me in terms of what is and what can we learn from playing with what is. And the other sort of piece of commentary that really got me thinking about this was from Andy Wilson at Graphics Interface when he gave a keynote. And he said that one of the things that they struggle with at Microsoft Research is the mismatch between what they have in the lab and what they can actually deliver as a compelling experience to end users. And I think the more we try and abstract away problems or believe that the world is going to be so different than it is right now, sometimes we get to the point where the things that we promise aren't necessarily the things that we can deliver. And HCI is not the only field that suffers from overpromising and under-delivering. An AI researcher could probably tell you something about that as well. So that's it for theory. On to some pretty projects and some pretty pictures. So smartwatches for rich, subtle gestural interactions. I'm really going to talk about sort of a series of projects, but grouped in three ways. And the three groupings don't actually follow that. They're more about sort of transient or rapid and quick interactions that you can do in everyday life, subtle interactions, and some work that we've done on reliability of gestural input, time permitting, in terms of steps that we've taken in order to sort of realize some of the aspects of theory that I've talked about. So the first The first sort of theme that I'm going to pick up is this notion of transient interactions. And it should be no surprise to everyone that displays are everywhere. Some of these displays we sort of see in everyday life. They're in our homes. Some of these displays we encounter more serendipitously in the world. And we want to support interaction with those displays. Or ideally, you know, if we really wanted a richly interactive world, we might want to support interaction with those displays. And so the simplest form of interaction is point-and-click interaction. And one of the things that Keiko and I sort of asked ourselves when we were sort of playing in this space was, how well could we do with a vanilla smartwatch in terms of supporting freehand input with an external display just in point-and-click interaction? So this is a standard task in HCI. It's called the ISO fits task. It's really boring. Participants love to do it. But essentially what we're doing is we're supporting point-and-click operations. And there's a couple of characteristics to the system that are pictured there in terms of how we self-calibrate the system. There is nothing augmented about the environment. The only thing we're using is a 9-axis generic IMU that is contained in the smartwatch in order to support that input and nothing else. So it's just off-the-shelf smartwatch supporting clicking, and that's all that we're doing right there. And so we built a little system like that. The video runs for a while. It just shows pointing and clicking in terms of the way that things work. Okay, so we built that system. There's nothing really shocking about that system. But what might we ask ourselves as a question? Well, we might ask ourselves, how well does this do against the gold standard in terms of supporting pointing and clicking interactions with freehand input? And the gold standard for pointing and clicking interactions with freehand input is a $20,000 to $50,000 Vicon system where users stand around and they put markers on their hand, and then they can point really reliably with low noise, and it's accurately projected, and it's got relatively great precision and everything else. And what we'd be interested in seeing is how well does this system perform if we actually invest a little bit of effort in building it compared to a Vicon system. And so we did that. Now the Vicon system still looks a little bit better there. Time is on the vertical axis, so low time is good. And so you can see the Vicon system is there in green. The watch system is there in blue. Those two lines are not statistically significantly different. I'm sorry about the lack of error bars on them, but there's no statistically significant difference between those two lines. So essentially what we've done in terms of time is we've started to come pretty close to a Vicon in terms of performance. Now the next question is error rate. How do we do compared to the Vicon in terms of error rate? And that was kind of even more fun. So this was work that was done on a 4-meter display with the user standing about 4.5 meters from the display. So a display that's probably a lot like that. And these target sizes are 1.6 centimeters, about that, on the display. The Vicon is in purple, and the watch point system is in green. And you can see that for the really small targets, we're killing the Vicon system. Something happened over here. I'm not sure exactly what. I have some ideas about it. But overall, I think one of the things you can see there is we're actually beating it significantly on error rate. And there are some reasons for that. Part of it is sort of engineering and looking at stability in small targets and how we can accommodate for them. In particular, sort of looking at what users really do and how these systems actually react. And this is hard to do with a Vicon because with the Vicon, regardless of how the user clicks, maybe they tap their other leg, maybe they point, whatever, there's no characteristic motion associated with clicking. The cool thing about a smartwatch, if you're actually supporting pointing with it, with either arm, is that when a user turns, they actually turn around an axis that's in the middle of the arm. And one of the things that happens is the watch itself falls and moves down to the right. So it just moves down to the right. And you can actually see that here in the click. When the user clicks, it moves down and to the right. But if we know that, those of you who know my past work know I did a lot of work on endpoint prediction and things like that in user interfaces. We can actually figure out when a user's slowing down and working to acquire a target. We can look at the click action that they perform, model it as a characteristic action, and we can backdate the click to the point where it actually makes the most sense so that we lower the error rate significantly. And so, this is sort of an example of what we've done in terms of comparing to the real world. And it sort of picks up that theme of beyond being there that I was talking about. It's not the only thing we've done. We've played in this space quite a bit in terms of 3D input with personal devices, whether they're smartwatches or smartphones. At Chi last year, we actually had a little bit of fun. Let me see if I can bring this up. So we basically looked at all of the personal device pointing techniques. We basically looked at, this is called a design space for personal device pointing techniques, using either the IMU or the touch screen, using one hand or two hands and looking at all of the devices, and we sort of divided this space up. We eliminated things that don't make sense, like one-handed interaction with a smartwatch. You can't really use the touch screen. You need two-handed interaction with a smartwatch in order to support pointing. That's why there are X's up there. So we basically looked at this design space of allowable input in this space, and we said no one's actually done any controlled studies to figure out which one of these devices are good. And so at Chi last year, one of my master's students just put all of these systems together and optimized them and basically created this sort of, performance time versus error rate space for these systems. And the useful thing about this is then, someone who wants to use these techniques can say, okay, well, what's the best technique? Someone who wants to do research on these techniques can say, well, what's bad about technique X, and is there any way I can accommodate for that in order to improve interaction? And so that, I think, sort of falls into this space of transient interactions. We're trying to support the most basic form of interaction in terms of you walking into a space and it being easy to interact with an external display. I don't do this, but the master student who was working on this work, he always used to give all of his talks using the smartwatch system that he'd actually built. And so he could use drag in order to move around the screen and point at things, and he could use rotate in order to click. And it was kind of neat that he could actually just demo that as he was interacting in that space. He could make it run. I struggle to make it run. It's because he develops a type of software that I like to call gradware. So, transient interactions. The next thing I want to talk about is I want to talk a little bit about subtlety and input. Anyone here seen Iron Man 2, Minority Report? Yeah, a few of you? Okay, good. Minority Report's sort of an old reference. Iron Man 2 is a little bit newer. These things come out all the time. You get someone who's using an external display. They're moving their arms like this, okay? That's both dangerous and tiring. You might hit someone beside you. The other thing is if you ever go to a senior's home and you look at interaction, I'm just mentioning this for you, Peter. If you ever go to a senior's home and you look at interaction, he's the one who keeps talking about retirement. If you go to a senior's home and you look at exercise classes, this is actually exercise classes for old people, okay? And so one of the things about building ubiquitous computing environments is if you want them to actually be used for a long period of time, it can't be a workout to use them. Standing desks aside, you really want people to be able to work for a long period of time. And if you don't believe that this is tiring, I invite you to hold your hands out, preferably in front of you so you don't hit anyone, for the rest of my talk, and you'll be tired. This is actually a phenomena that we're familiar with in computer science. It's called gorilla arm. And people have actually characterized, the cost of, sort of like interactions with freehand input. And the way that they've done that, sorry, this is not my work. The way that they've done it, it is Canadian work though, so that's good. The way that they've done it is they've actually looked at the center of mass of the arm. So the more you have on your hand, obviously, the more the center of mass moves out. They've looked at the distance from the shoulder. They've modeled that as torque, and they figured out how much effort it takes. We've actually seen this in work that we've done in the lab in pointing interfaces. You can see someone here using a Wiimote in order to point. We call this the Wiimote effect because of that. If you've ever played a game on a Wii, you're familiar with this. You start out playing tennis, and you're playing tennis, and then you get good at it, and you're playing tennis. And the reason that that happens is because this is less effort than this. It's faster and it's easier. And so the question that we asked, is if this and even this results in effort and consumed endurance, then what happens if we look at this where the arm's at rest? What type of interactions might users want to perform in this space? How rich of an input space can we support in this space? And what else can we learn about this form of interaction? So this is the part of my talk where I sort of, devolve into HCI a little bit, but just to show you a video of the system to distract you from all of the HCI stuff that's coming. Here's the system working. People are drawing sort of little palm graffiti bigrams and trigrams at the side of their body. It's a really quick clip, but essentially you can sort of see down the person's leg right there, and you can see the system tracking the input and capturing it. And then there's a little naive recognizer based on dynamic time warping running in the background that's recognizing unigrams, bigrams, and trigrams in palm graffiti space. So what we were interested in this space is sort of the design space here. And we used an HCI technique called an elicitation study. And that's just a fancy word for asking people how they would do something. The reason that we do this as HCI researchers is to try to understand what makes sense to users. It's not necessarily the case that we're going to use those gestures, but in the discussion between what an AI person who's studying recognition and a user might want, that discussion where the user's concept of what makes sense and the AI researcher's concept of what is possible can intersect in order to produce a system that is probably better than another system. So I'm not an AI researcher. I consider AI something I consume, but I am an HCI researcher, so I'm interested in how people might conceptualize interaction. And so there's a lot of boilerplate up there in terms of standard techniques for calculating agreement score and everything else. The output from this is actually, I'll just skip over that. That's tasks. It's kind of boilerplate. The output from an elicitation study is basically, kind of a concept of how users agree in terms of interaction spaces. But more generally, just to break it apart and talk to you about what we're trying to get out of these things, here's just something pulled out of this. It's a favorite item. And when we ask users to describe a favorite item, they do a bunch of things, in this space at their side. They draw a star. They draw an L for like. They put a box around it as if they're checking something. They put a heart next to it. They actually check something. They write out a word called star. They put an F with a circle around it. The important thing about this is if you look across this space, what you see a lot of ideographic and alphabetic characters, and you don't see a lot of pointing, because it turns out for a user, if they're going to point at the display, they're just going to point at the display, and this space actually makes sense in terms of ideographic and alphabetic input, at least for a bunch of people that we had in lab that we analyzed this space with. And so we actually played with that a little bit. We looked at performance based on naive recognizers. We concatenated bigrams and trigrams together. We looked at reject rates and a lot of other things. We looked at training. And I'm not going to go into the results in general. I'm just going to leave you with this notion of sort of the n-gram-based input, because I've only got, I guess, about 7 minutes left.
No, that's not right.
That's not right? I've got more time left?
Yeah, like 20.
I have 20 minutes left. So I don't have the slides here because I deleted them out, I think, which is too bad. But I could have wasted a little bit more of your time. But maybe we can chat a little bit at the end. We'll see. So anyway, that's sort of this notion of the subtle input space, and subtlety is useful for a couple of reasons. It's sort of the reasons that I talked to earlier in terms of effort. It's also the issue of what researchers in HCI call social exposure, as a little bit of a double entendre. But it's this notion that if you're interacting in the real world, you don't necessarily want to be that obvious about interacting. It looks kind of strange if people don't know what you're doing and you're moving your hands around. And so that really brings us back to this sort of subtle space. So the last thing I want to talk about is I want to sort of pick up this thread of the DTW recognizer running, and I want to talk about some of the work that we've done on reliability. I did preface this by saying I'm not an AI researcher, and that is in fact the case. And so what I'm not really interested in here when I talk about reliable input is I'm not really interested in maximizing precision and recall necessarily. I'm interested in maximizing the perception of reliability of the systems that the users are doing. And the question that you might ask is, isn't that the same thing? And what I'm going to tell you here, and then what I'm going to show you using this thing called data, is that it's not. That you can take two systems that are equally reliable and users will react to them differently. And a lot of that is based on the way that you actually understand how users are interacting with the system, and you model errors that users commit in the system. So I've talked about subtle input. I've talked about transient input. One of the things that should be clear at this point, or hopefully can become clear, is that there is some recognition that we need to do in this space. And the recognition is actually a challenging problem in this space, in part because of the subtlety of input, but in part just because the characteristics of motion gestures. And the types of motion gestures that make sense to users and that people want to do and that people can do reliably. So I'm just going to talk a little bit about the recognition challenge. And in order to do this, I'm going to arc back to some early work that I did with Jamie Ruiz and Yang Li. It was published at CHI 2011, so it's actually relatively old work right now. But what we did is we looked at the design of motion gestures. And one of the big takeaways from that, it was actually an elicitation study, and I've already told you what an elicitation study is. But one of the big takeaways from that is that gestures tend to be, gestures that we elicit from users tend to be simple, discrete gestures involving one, maybe two axes with low kinematic impulse. And these things make sense when you think about it. So it's easier to remember a short gesture, like a check mark, than a long gesture, like a squiggly line. How many times did I go around? I have no idea. So they tend to be simple, discrete gestures. They involve maybe one, maybe two axes of input. And the reason that they do is because you start to do gestures. One axis is easy, two axes little bit harder. If I'm going to do right angles between two things, it's easy here, it's a little bit harder here. As you add more axes, sort of the deviation gets a little bit harder for users to figure out. And they tend to have low kinematic impulse, and this should make sense for you just from a fatigue perspective. If my motion gesture is moving my hand to the right, and I move it to the right like that, it's a heck of a lot more comfortable than if I move it to the right like that. One takes almost no effort and is very comfortable to do. The other takes a lot of effort and actually hurts my arm more and more and more as I get older. And so one of the challenges with this in terms of recognition is that if we want to design these sort of platforms for input in ubiquitous environments, the types of inputs that we're supporting in gestural space are actually the types of input that mimic everyday movement of the device when people are using them. And that's actually a challenge that we need to overcome. And so there are lots of ways to overcome those challenges. And we've sort of looked at all of these ways for overcoming the challenges. But the first two in particular do have liabilities associated with them. So one of the things you could do is you could come up with better gestures. The double flip is an example of a low-effort gesture that almost never occurs in the real world and is easy for someone to master. That's one of the reasons that Motorola grabbed it and rolled it into their system. Motorola also has the karate chop gesture, which is a little bit more effortful in terms of interaction in order to turn on a flashlight. And I think they've got a few others besides. But you start to, if you want to support a large gesture set, you start to run out of gestures that actually make sense relatively quickly, or at least I do. Another thing you can do is you can use delimiters. So the idea behind a delimiter is you take a gesture that's relatively rare and you say, you always have to do that before you perform another motion gesture. You essentially make every gesture into a compound gesture. That works. That is exactly what Jamie and Yang suggested that you do with double flip, is you make it a delimiter for motion gestures. So you always do a double flip and then you do your motion gestures. But always doing a double flip and then doing a motion gesture is awkward. And doing a double flip to switch to motion gesture mode, that introduces modes in the interface, and there are well-known problems with modes in terms of people remembering them. And so one of the things that we've been playing with is sort of recognition strategies, tighter thresholds, and their effect on users. So for AI researchers in the room, this is boring. I want you to go to sleep right now. But one of the things that I told you for non-AI researchers is that the likelihood of observing movements sort of increases as you go across this space. And if you sort of look at this space, the gestures that we tend to want to design are gestures that sort of coincide with everyday movement. And there's a standard way in order to boost precision associated with that, so you don't have a lot of false positives, and that's to tighten thresholds. The problem is when you tighten thresholds, you suffer from a problem of recall. It's harder and harder for users to hit these gestures precisely. If they need to move at a certain rate with a certain orientation, they start to create errors in the system. And so you've got this trade-off between precision and recall. And one of the things that we asked is there a way that we can preserve both high recall and high precision when gestures collide with everyday motion? And in order to talk about some of the work that we did in this space, we were conducting some in-lab experiments on motion gestures. And we had users walking around, and they were performing motion gestures. And we had tightened thresholds so that there were no false positives. It was actually, if you think back to the slide where I described all the motion gestures, there was, when I was talking about the cognitive cost of motion gestures, you may remember there was a slide at the first, and I said we did a bunch of work on design and cognitive cost. When we were doing that cognitive cost work on motion gestures, we had people walking around in a lab around a path that they needed to follow, and they were performing motion gestures along that path, and we were tightening up thresholds so they didn't get false positives. And so because we didn't want false positives, we were actually losing on recall. People would try and do a gesture, and they would miss, and they'd need to try again. And we noticed something interesting in this space. So if people are going along and they try a gesture and it doesn't fire, they try the gesture again. Don't even stop walking. They just try the gesture again. If it doesn't work, then they look at the phone and they try it again. And if it doesn't work, then they stop and they start to do weird things with the phone. They shake it, they tilt it, they move it on a different angle. They do something with it, sort of this annealing in the space to try to figure out what's going wrong. And so we said, this is kind of interesting. If you start to think about, attempts and the cost of, it's not errors, but the cost of failed recall, rejects, the cost of rejects, maybe we can't do anything about attempt one, but what if we start to look at actions as a sequence of actions in this space? How would that affect users? What would their perception be of that? And so this is actually a little bit difficult to do, I'll talk about some of the work that we did on this. But this is where I get into the distinction between reliability and perceived reliability, and that's essentially what we're talking about here. So the way we did this is we built just a simple little bi-level threshold gesture recognizer. I don't know if there's anything really that shocking in that. It's just based on observations that if a user doesn't succeed, they try again. And it's just, it's based on the same principle as you double click on an icon. If the file doesn't open, you don't throw your computer on the ground and jump on it, you click on the file again. It's not really that shocking to anyone. This is sort of a single gesture, double gesture, you can go on, but it's not actually that hard to implement. And so we did some work evaluating bi-level thresholding. We wanted to look at reliability versus perceived reliability. That's work that we published at IUI 2017. And then we wanted to look a little bit more at behavior on richer gesture sets. That's a paper that's in press in ACM Transactions and Intelligent Interactive Systems. This one you can't get yet, and it's disappeared from ACM TIS webpage. If you're ever interested in the work, you can ask me or Keiko for a preprint copy. But anyway, in terms of looking at user action, we actually started out by conducting a walking study in Davis Center a couple of years ago. And so we actually had a portion of the hallway right up there in front of the HCI lab cordoned off. People were walking back and forth in a real-world environment. We had researchers at either end just to, hopefully avoid like collisions and things like that. But we allowed people to walk by, so we had distractors in the environment. And what we did is we built a type of recognizer called a Wizard of Oz recognizer. Has anyone heard the term Wizard of Oz? Yeah. Everyone know what a Wizard of Oz recognizer might be? I see a bunch of people nodding. It's essentially you're simulating recognition. So what we did is we didn't have an actual recognizer running, but we simulated it by prompting the user for input and then looking at the, essentially like a forced choice recognition problem. We say, did they do the right gesture? And then if they did the right gesture, we started to artificially manipulate recall rates simply by dialing them up or down. Does that make sense? So like essentially what we would do is they would do it, and if they were in the space, we would say, okay, what is our recall rate, and where are we in this space? And if the recall rate was like 60%, we'd say, okay, we want a recall rate of 60%. That's interesting. We're not going to take this gesture regardless of how well they perform it. And then they go again, and they perform the that we want, and it's still inside that space. We say, okay, 60%, we'll take this gesture. So essentially what we did is we manipulated recall rates so that we could measure their perception of error. And we fixed recall rates at different levels. Some people may complain about these different levels of recall. If you're complaining about these different levels of recall, I do have another slide that shows that recall on single instance interaction for some of these gestures can be as low as 30%. But anyway, we manipulated recall rates like this, and we ran a type of psychological experiment called a just noticeable difference experiment. And the way that we did this is we did essentially a within subjects experiment on recognition rate with recognition rates as between subjects factors. And so that's just so that people are getting exactly the same amount of work for two different recognizers. They still have to do 70 gestures in order to get 50 correct, or 82 gestures in order to get 50 correct, or 100 gestures in order to get 50 correct. It's just the strategy that we've got is different, and we wanted to see whether there was a difference in perspective on that. And we used an instrument on that called the NASA Task Load Index. It's a measure of cognitive workload. You come up with a weighted workload score, and you basically look at the weighted workload and you say, if there's a statistically significant difference in weighted workload, you can go down and you can figure out why users perceive that there's actually a difference in workload or a difference in effort between the two systems. So we actually use that standard instrument in HCI. Lots of people use it, but the cool thing about this is if you look at the fixed versus the bi-level threshold, you can see that the bi-level threshold has a lower workload score to a statistically significant margin, and it's really based on performance. Users actually think that these two systems, despite the fact that the recall rate is exactly the same, the effort that the user needs to put in is exactly the same, they perceive it as being a different amount of effort. And so that's, I guess, the big takeaway from that. We also looked at user preference. This was kind of interesting. One of the things about the 50% rate, the 50% rate was more evenly split. One of the things about 50% recall is it always fails the first time and always succeeds the second time. And users actually notice this, and so you can see kind of the ambiguity over here where fixed actually does better. And we actually thought that as we get up to 70 or 80%, particularly because, well, 70% definitely, particularly because errors are relatively rare. Long sequences of errors are relatively rare when you've got 70% recall. One is common, but two is long sequences of recall, missed recall are relatively rare. We thought this would converge, and in fact, you've got the strongest preference right here for the bi-level thresholding as compared to the fixed level thresholding. If you want to talk about experimental design, this experiment was poorly designed, and it was poorly designed because there's an indifferent option. If you're ever running a user preference study, never put an indifference option. It's called forced choice, and if it's 50-50, that means there's no difference. This is shared work. So the other thing that we did with this is we actually looked at larger gesture sets. So we played with hand gestures with this system. And one of the reasons we played with hand gestures is because hand gestures have very subtle differences between them. And so we came up with a set of 27 hand gestures. And this is sort of the first effort that we spent on building some hardware. The hardware is actually back there on the table somewhere. But we put some hardware together, and we built a little system that supports capturing hand gestures, and you can sort of see the system running right here. And it's just sort of running in terms of recognition mode. And basically what we did is we actually looked at this system in terms of precision and recall and how well bi-level thresholding could help in terms of precision and recall. So as we tighten up initial thresholds and then we look across the system, how well does this work? So the important thing here is the thresholding is basically a ratio between the most probable and the next most probable category in a probabilistic recognizer. That's what the 2.7 represents. 1 over here essentially represents forced choice. So if two categories are equally positive, you're sort of in a forced choice condition. If you're running this in bilevel thresholding mode and you don't hit the tight threshold, then you need to go back into the other mode. And so you can do sort of a forced choice where you need to see two possible gestures in order to recognize it, or you can actually boost this, and that has sort of small benefits in terms of precision up there on top, and you can sort of see its effect on recall right here as it falls down on this axis. So anyway, just to conclude, because Dan said 3 minutes or 2 minutes or something like that, I talked a lot about wearables and their use in terms of supporting rich, reliable interaction in a transient way in ubiquitous computing spaces. And just to wrap up and tell you why I'm talking about this, if you think about wearables, they're a really intimate device. They know you and they can learn a lot about the world around you. And so the reason I think it's compelling from that perspective is, you can start to build up a vocabulary of interaction with these devices that you master, that you can then use to interact serendipitously with computation in the world around you. And it's kind of the other side of larger devices like smartphones, where they're really useful for interacting with things that are far away, information on the internet, emails that you need to send to someone. A smartwatch, because it's always there and it's always available, it's something where you can walk into the environment and you can just start to use it. And so sort of wrapping everything up, I think that's kind of the view or the benefit of using smartwatches in this space. That being said, thanks for your attention. I really appreciate it. Kudos to my research group for all the great work that they've done, my collaborators in France, and my collaborators at Waterloo as well. Are there any questions? Yeah, go ahead. Yeah, it's all been done before, and yeah, it's not. So you can put an "and" in there if you want, right? Like, because we do gestures doesn't mean that speech is horrible and we should never do it. But on the other hand, there are well-known problems with speech as well. In the present, accents can cause it problems. In the future, if you start to look at, public environments, for instance, serendipitously encountered richly interactive spaces, are we ever really going to be able to solve the, problems of background noise and signal-to-noise ratio that exist in those spaces? Who knows? I think the answer is that there's a time and a place for speech and a time and a place for gestures. I happen to be working in gestures. That doesn't mean don't work in speech. So if you are, my intention here is not to say that I don't respect your life's work. It's to say I do something else, and that's all. Yeah?
So I guess this is kind of an unfair higher level question.
Ask unfair higher level questions. I'll treat it like a hiring committee, even though I never need to do that again.
So I mean, this whole approach is humans instructing computers. But when you turn this around and say, well, let's take a list of all the applications where you want this. We've made a lot of progress in vision and speech understanding, all sorts of stuff. And so if you turn this around and say, well, what applications can we just solve by saying that the interactive system will understand what the human being is doing without any special gestures or without any wearables, blah, blah, blah.
Yeah.
I mean, how much ground does that cover? Because like you, I don't wear a watch and I'm not, it take a lot.
Yeah, no, I don't wear a watch. I hate them, right? Like, generally,
There's a lot of ambiguity
Yeah.
in gestures that you're saying, so it's
yeah.
also a little socially embarrassing in lots of cases to be doing funny stuff.
Yeah, no, I think that that's a great point. Like, you're sort of asking, you've got this space of applications that exist and ways that we can provide input. How much can those applications infer about what we want to do? The inference aspect, and it sort of arcs back to the point that I was making on the Midas touch phenomena. The inference aspect is still challenging in this space. Whether it's, two people in this room both opening their laptop and starting a presentation, which one actually gets the projector, or it's, I'm trying to think of a good example off the top of my head, and I can't necessarily pull it in. But if you think more generally about, particularly these ubiquitous and sort of richly interactive spaces, I think you do brush up against the limits of inference in this domain in particular. And so users want to feel like they're in control of the environment. You know, you walk into a room, do you always want the lights to come on? No, obviously not. If it's the middle of the night, you may just want to walk to the fridge and get, you know, a glass of something, or you may want the lights to come on. And I think that notion of sort of balancing explicit and inferred interaction, you know, I wouldn't say don't infer. I would say infer as far as you can, understand errors, and then develop techniques in order to allow users to avoid errors as much as possible and to always feel like they're in control of the systems. So I don't know if that really answers your question. But.
By this inverse approach, you still have errors. But you know, if you say you have control because you can do something to override or negate what the system decided to do, you retain control. You don't have to do anything special except when it gets it wrong.
So can you repeat that again? I just, no. So I think,
I think that
yeah.
you retain a sense of control if you can say no.
That's right. Yeah, it's, and so the tension that you're talking about is really one of error recovery, right?
Yeah.
Versus,
You infer and then you
yeah, versus reactive. Would that be fair?
I would say it's, am I controlling and then sometimes it misunderstands, or is it just doing, is it in WIMP mode and I'm saying, no, you got it wrong?
Yeah, no, so I think that that's a great point. And it may be the case that AI researchers will get to the point where the systems that they design make errors much, much less, just inferring what people are trying to do and reading their minds, than systems that look at what the user is actually telling it and trying to infer action from that based on their interpretation of whether the user is being explicit in order to issue a command to them, or they're just, you know, for instance, in this case, gesturing because they're gesturing. Like it may be the case that I don't need to do anything. I can just walk into this room and my presentation appears on the screen as an example. Or it may be the case that, you know, I still need to do some work. I think, you know, the answer that I would give to that. Yeah, you walk up to the podium, that's right. And I think that the answer to that is that we're not there yet. And so, you know, it's all right to approach these things from two directions. One being, how can we design systems so that users increase their ability to fluidly express things in a rich way and in a reliable way to the system? How can AI researchers continue to infer what people are doing? You know, again, it kind of goes back to the answer to Peter's question. You know, we can do both of these things, and we can figure out where we want to partition the space into things that happen automatically and into things where the user needs to provide a little bit more guidance. And it doesn't necessarily take anything away, I don't think, from either side. Right? Like, I'm not saying I'm solving every problem in the world. I'm taking one vector into it. You know, Pascal or Wayne or, you know, someone else who's doing a lot of machine learning here may take another into it. If we meet in the middle, that's okay.